Okay.
Welcome everybody here. As Nilima indicated a few minutes back, we are starting this new webinar series on behalf of the ICICLE, which many of you must be knowing. It's an NSF AI Institute. We are operating on the fourth year of the institute, and as a part of that, we have focus on digital agriculture, focus on animal ecology or smart fields, and also focus on food security and distribution. And of course, the main focus is on the intelligent cyber infrastructure. So as we have been developing solutions for not only for the cyber infrastructure, but enabling all these domain places, we have also been starting to release some of the software components, and people have started using those. So the one of the main objectives of these webinars are to indicate to all of you like what are the software components, where you can actually download, and basically we want to get engaged with the community. So this is our the first one, and Professor Hari Shoromani, he's leading the digital agriculture component or the area of the institute, so he will be taking care of this presentation today. So let's give a big welcome to Professor Hari Subramani.
Thank you. So, as was mentioned earlier, the ICICLE AI Institute is aimed at creating cyber infrastructure solutions which are powered by high-performance computing and artificial intelligence to tackle challenges in various domains like agriculture, ecology, and food systems. So in this talk, we'll be describing some of the let's say domain drivers. So what are some of the challenges in agriculture that we are facing today? How can science, computing, and AI help address those challenges? And how can we create software which everybody can use, not just a few, which everybody can use? Basically, can we democratize it and make it available for everybody, and with a low barrier and cost of entry? So that is what we are trying to describe here. So overall, the talk will first describe some of the challenges that we are facing in agriculture. We'll describe how AI and HPC can solve those challenges by creating a workflow or a pipeline, and how you, the user, can take advantage of that pipeline on various supercomputing systems like the San Diego supercomputing system or the Ohio supercomputing system here at Ohio. So that is the overall outline of the talk. So if you look at the challenges, there are a lot of people on this earth. And unfortunately, we don't have enough food to feed all of us. And typically, if you look at it, the expected yields fall a lot below what we expect to have. Okay. What is the reason for this? And how can science help here? So that is one of the challenges. The second challenge is that to create a sustainable agricultural workforce, we need to train the next generation of professionals to use technology. And how can we democratize this technology so that everybody, not just a computer scientist with a PhD or a professor in food systems research, can use it, but can your agronomist use it? Can a data scientist use it? And eventually, can a farmer use it? So those are the challenges that we are trying to tackle as part of this work. Now, all of this is driven by agriculture and food. So what does a farmer want to know? So let's say if we look at a field like this, the first question is, hey, is this a healthy field? Will this give me a good yield at the end of the growing season? That's the high level question. But we need to break this down. If you take a large field like this, there are a lot of sub problems that you need to solve. So if you take it individual plants, is this a healthy plant? Is this healthy? So in this particular case, we are taking soybean, which is by far one of the most, let's say, grown crops in the United States. So a soybean crop can have a lot of issues. It can have defoliation, it can have blight, it can have nutrient deficiency, so on and so forth. So can we use artificial intelligence? So all of us know that image-based AI techniques have been proliferating over the last decade. And we need a lot of computing to do this. So can we apply any of these emerging technologies to this real problem in agriculture and find answers to questions like, hey, what portions of my field are defoliated, so that we can take precision action instead of doing a blanket application of chemicals or fertilizers or fungicide or weedicide, which is going to result in a lot of dollars wasted for the farmer and a lot of environmental and ecological impact for the community at large. So broadly, what we are trying to create here is smart cyber infrastructure for democratized digital agriculture, where users can do crop health diagnosis to take management interventions. Like, suppose if I have defoliation or crop blight or nutrient deficiency, can I apply fungicide, herbicide, weedicide, fertilizer to alleviate that particular problem? But there is a huge gulf in the necessary cyber infrastructure or software ecosystem to translate this crop health diagnosis into crop management interventions. And this is where ICICLE comes in with high performance computing and modern AI enabled solutions to allow farmers, agronomists, data scientists, and a lot of other stakeholders to convert this set of problems into a set of solutions. If you look at AI-driven digital agriculture, you have data being collected in the form of drones or tractors. This data can be multimodal in nature. You can have images, text, tabular data, audio data, visual data, so on and so forth. So satellite data. So can you collect all of this data into a central location, process it using modern neural networks or AI techniques, and convert it to a simple prescription that can be turned into actionable, let's say, information on the farm? To summarize, we are trying to answer this broad challenge. Can we create intelligent cyber infrastructure for the computing continuum, not just on the cloud or on some server room, but can we span the computing continuum from on-field sensors to near-edge or far-edge devices to the cloud, as well as HPC systems, and democratize the benefits of AI to a wide spectrum of stakeholders? So this is where the smart CI that we have created comes into picture. So as I mentioned, we have partnerships, farmers, or co-ops trying to tackle and address various crop health issues. Like, do I have enough residue cover on my soil to make sure that I don't have erosion over the next season? So how do I figure this out? And what is the action I need to take? So if I don't have enough residue cover, or if I have too much residue cover, maybe I want to remove some. But how do you go from this particular requirement to this particular intervention? So how do you convert this crop health diagnosis to a crop management intervention? So that is where our workflow comes in, by using high performance computing and modern AI enabled solutions to collect data, process data, transform that data into actionable information for on-field management techniques. Now, we are not the only people doing this. There are other vendors doing this in the field as well. But why did we choose to do this nonetheless? So what we want to address is a widening gap between AI-driven products in agriculture and the emerging needs of all agricultural producers. So if you look at large vendors like John Deere or Trimble, or those kind of very large scale industries, they only focus on green technology. That is a system that can detect weeds in a green background. But this simple system itself has led to a reduction of 70 to 90% in herbicide application. Further, they only have focused on cash crops, soybean, corn, and cotton. But that's not the only crop that is grown in the United States or across the world. So very little work has been done to expand beyond this particular system for various crops. The main reason here is the lack of software infrastructure for collecting, transmitting, curating, training, and inferring on all of this data and converting that into actionable items. So this is the main challenge that the cyber infrastructure that we are trying to create is trying to address. Now, all farms are unique by geographical location, crop, tillage regiment, equipment, etc. So the solutions should also be unique. Unfortunately, the large industry partners that I mentioned lack either the bandwidth or the financial incentive to tailor solutions to the needs of individual farmers. Okay? So what we want to create is an AI-powered, HPC-enabled, easy-to-use cyber infrastructure pipeline to collect, process data, train models and infer using those models on this data, and convert that into actionable intelligence for on-field use, with the goal of improving the production efficiency, enabling optimization of crop production, and improving the overall profitability and environmental and reduce the environmental contamination by democratizing all of these resources for the larger population. Now, what are some of the key differences between what we are doing as well as what others are doing? So we are trying to create workflows through low-cost public access hardware and simple and composable interfaces which can adapt quickly to the needs of the end practitioners, compared to what other solutions like Microsoft FarmBeats and large industry organizations like John Deere and other ag-tech companies are doing. So with that, this is the cyber infrastructure pipeline that we have created over the last few years with our partner organizations. So as you can see, this has various components and there are appropriate cyber infrastructure releases and software associated with each one of these steps, which I'll go over through the remainder of this talk. So you have steps for data collection, movement of data from the far edge devices to the edge, edge to the cloud, cloud to the cloud, and also for data pre-processing at the edge and the cloud, and all of this with authentication and appropriate orchestration capabilities. Once we have the data, we figure out how to train new AI models using that data, infer at the edge and the cloud using those AI models, and generate actionable intelligence for farmers to use for on-field inference. The various software components involved in this overall workflow are listed here. All of these are being worked on by various ICICLE partner organizations around the country, and various releases have been we have almost made 8 to 9 releases of all of these components put together over the last several years, and more details of these releases are available towards the end of the slide deck. So the main components involved here are one, TAPIS for overall authentication and orchestration of the various pieces. So this forms the underlying fabric. We have Globus-based file transfers for moving data from the edge to the cloud. We have OpenPass for data collection on the edge, as well as transferring the data from the edge devices, the far edge devices like the drone, to the edge. We have the ARA wireless infrastructure from Iowa, which is the data transfer backbone to move data from drone to the edge as well as edge to the cloud. We have ArrayMorph to optimize data transfers from cloud to cloud. And we have Harvest for performing high-performance training and inference, as well as the final visualizations and generating the prescriptive answers for the farmers. So all of these components, software components put together, forms this digital agriculture pipeline that you see here. Now, over the rest of the talk, I will go over the pipeline and describe how various components fit into this pipeline and how all of that put together becomes more than just some of the parts. The first step is always data collection. So you can either fly a drone or drive a tractor on your field to collect this data. Now, once you have collected this data needs to be moved. But before that, this is an example of how OpenPass can help in collecting the data. So we can maybe suppose you are a farmer, you drive your pickup truck to the farm, sit on the load bed, take out your drone, set up a waypoint, just like you would draw a route on Google Maps, you would set up waypoints for your drone to fly. And based on those waypoints, your drone would actually fly across the field and collect data at various points, transmit that data to your edge, and begin processing at the edge if that is what you want. Now, the image capturing is also done by the OpenPass and moved to the edge devices. The data transfer from the far edge devices to the edge devices can happen through multiple methods. The first one can be through the ARA ICICLE integration, which allows us to gather and transfer data through the ARA wireless, which has been deployed on various farms at our partner organization at the Iowa State University. So here the drones have been equipped with cameras and computers and wireless radios, which gets transmitted over the ARA wireless to an edge computer, which is then uploaded directly as a streaming service to the cloud and made available to all of our end users. So once the data has reached the edge from the far edge, we have other techniques to move the data from edge to the cloud or from cloud to cloud. So we have Globus-based file transfers. So imagine this scenario. You have a drone pilot who's flying the drone. The pilot may not be a very accustomed or accomplished computer science person, but he or she is very good in flying the drone and collecting the data. What we have created is a software module which can be deployed on a laptop, and where the pilot can copy the data onto a particular location, which will trigger the entire pipeline that I described here. The first step of which is to use Globus to move the data from the edge laptop to the cloud. Once the data has moved to the cloud, then we can begin the first step of data pre-processing and also data movement. So suppose you have the example of satellite data. The satellite data is mostly stored on Amazon S3 buckets. But what if I want to do my processing on the San Diego supercomputing system or the Ohio supercomputing system? Now, when you have a huge image and a high resolution image, it is big in terms of size and also big in terms of detail. The end user may not need all of those details. So for instance, if you take a look at this image, this is my area of interest, which forms maybe about roughly 25% of the overall image. But we end up transferring the entire image, which is a waste of bandwidth. So can we selectively choose what is our area of interest and just transfer that? So ArrayMorph, one of the components that ICICLE has developed and released, is capable of doing that. So instead of transferring the entire image, it is able to just pick the necessary area and cut off all of this rest, so that we are able to reduce the overall data being transferred over the network. And as you guys may know, several times it is cheaper to just FedEx a hard disk with the data than to move the data actually over your internet. So having this kind of pruning capabilities is very important, especially in this era where we can quite easily collect terabytes of data in a few hours when you go out onto a field with data capture equipment. So ArrayMorph is able to move the data faster and cheaper, almost 1.5 times faster. And this also leads to a significant reduction in the amount of money you need to pay to these cloud service providers who charge you for ingress and egress of data. Once we have the data captured, and move to the correct high performance computing location, now we can begin manipulating the data. So if you are capturing images, you want to be able to make sure it is in the correct aspect ratio and be able to see what exact GPS coordinates or physical location the data belong to. So this is where we do geotagging and rotating the data so that it is at the appropriate angle for visualization. So this shows the pipeline for the UAS information extraction. So once you have large data like this, it is geotagged and rotated into appropriate sections, and the actual images are extracted from that. And these images are put together in terms of plot tiles so that we are able to visualize that better. Now, if you want to do this at scale, you need some GPU resources or high performance computing resources there. And that is why some of these tasks are being done on the HPC systems or cloud computing systems. And imagine if you want to do this for hundreds or even thousands of flights on a yearly basis. So you need to have a lot of computing power behind this. So far we have collected the data, moved the data, and transformed the data. Now we are ready to train the model. So we have a flexible pipeline, and this is where the harvest component that I mentioned earlier comes in. We have a flexible pipeline which allows us to select from a bunch of pre-trained models from a model repository, which is what you select here. You can point that particular model to a particular data, saying that, okay, this is the data that I want to do the pre-processing on. There is a bunch of hyperparameter selection options, but most of these do come preloaded with the best options. But if you are an advanced user, we do have the ability for you to change some hyperparameter settings like learning rate, batch size, labels, number of epochs, number of GPU, so on and so forth. So the idea is that you don't have to figure out how to actually orchestrate the high performance computing based deep learning job on the supercomputing system. All of that has been taken care of for you with industry's accepted best practices. You can select that and trigger that from an easy to use user interface. So then we select the appropriate model that we want to. You can use one of the pre-trained models that ICICLE offers, or bring your own model, so to speak. Now, one of the biggest challenges with any data curation is labeling the data. I can easily collect terabytes of images, but for me to label those terabytes of images is extremely time consuming. So we have created semi-supervised as well as unsupervised techniques, which allows end users to label a fraction, less than 1%, or a few dozens or hundreds of images from a data set of like thousands of images, so that we are able to use AI techniques to reduce the burden, data labeling burden from end users. So once the labeling has been done, we use HPC resources at sister institutes like the San Diego Supercomputing Center, the Ohio Supercomputing Center, or cloud resources to start the training job. The training may take a few minutes to a few hours, depending on the size of the model and the size of the data. Once the training is done, the system allows you, the user, to download the trained model, download the labeled dataset, and access our inference, our homegrown inference tool to generate the results of the um, training, so that you can create it for your own use. And all of this is done with complete security and privacy. So whatever data is being used here, whatever model is being generated based on the data is completely yours. Nobody else will be able to see that. Now, if you are a more advanced user, we have the ability to look at some of the training statistics as to how much time it took, what is the average time per epoch, what is the accuracy, what is the precision, so on and so forth. Now, the next step, now that we have collected the data, moved the data, pre-processed the data, and done the training, is to perform the inference, so that I can create actionable information for taking decisions on the field. Okay. So once you have this data, now we can collect more data from the field, or like from drones or anywhere else, and try to see what exactly that the drone or the image is showing us. So this is where again OpenPass comes in. So OpenPass can be used to capture images, pre-process them, as we demonstrated earlier with creating the plot files. And on the inference side, we would use one of the pre-trained models, or the models that we just trained, and start the inference. The inference itself can take some time, depending on the number of images that we are hoping to infer. And the system will tell the user how much time it is expected to take and when it is expected to complete, and will send a notification to the user when the inference job actually completes. And the user can look at the result of the inference and say how many, for instance, if I want to look at the growth stage of crops, the system will tell that, okay, out of this field, let's say 30% is in growth stage 1, the rest is in growth stage 2, growth stage 3, so on and so forth. So the overall workflow for the inference visualization looks like this. The training team would have uploaded an appropriate model to the model repository. The end user will then get the model from the repository and apply that model on new data from the user interface. This request is sent to the web server where the inference can potentially happen if the model happens to be a large model. The result of the inference is downloaded and moved to the edge device, and from there it can be passed on to a far-edge device like a drone or a tractor. So once the inference is done, now we want to generate prescriptions or other visualizations which can allow the end user, who could be a data scientist, a researcher, a faculty member, a grad student, an agronomist, or a farmer, to see what is the current stage of different crops on the farm. So in this visualization, we are seeing various plots in our test fields, and we are trying to demonstrate what is the growth stage of the various crops. So each one of this is a plot uh, which was whose image was captured using a Wingtra drone, and we are classifying all of these different plots based on growth stages. So the heat map is shown here. So we have growth stage 1 through 16. So they are split into different buckets. And we have a nice visualization here which shows that all of these greens are this particular growth stage. Okay. So that is a high-level view. If you want to have more in-depth views, you can click on any of these individual components, and it will show you a sample images from collected from those particular geographical locations, and it'll also tell you why we made that prediction for that particular image. If you have multiple fields around the country or around the state or the city, then we have the ability to show markers on a map kind of an interface, very similar to Google Maps, so that you can click on one of these red dots, which will take you to an image like this. You can click on one of these boxes, which will take you to another image like this. So you can go from a very low granularity to a very high granularity as well. Finally, if you want to take actionable items, or let's say actionable intelligence, we also generate a shapefile. A shapefile is nothing but a JSON formatted file with labels and GPS coordinates, which tells smart tractors where to go and do certain actions, for instance, like spray herbicide, fungicide, or weedicide. So these shapefiles are generated by the pipeline, and these shapefiles will be fed as input to smart tractors. Smart tractors, once they go to that particular location indicated in the shapefile, it can trigger certain actions, for instance, turning on a spray nozzle. Okay, so this is how, using the ICICLE's symphony of various cyber infrastructure components, we are able to collect data, move data, pre-process data, train a model, infer using the trained model, and convert that to actionable information for on-field actions. So this is an overview of the overall ICICLE cyber infrastructure components that we have created. The various components that I mentioned earlier have been released several times. These are some of the latest releases of the components: the TAPIS component, OpenPass, ArrayMorph, and Harvest component. For a full list of the releases, please go to this particular link. So I first want to give an overview of the various components that are involved. So this is that particular overview. Now, the obvious question is, how do I, the user, take advantage of it? Okay. Okay, now I want to go to San Diego Supercomputing Center. or the Ohio Supercomputing Center? How much storage is needed? How much compute is needed? How much money will be spent? How much time will be spent? How can I use this? So that is what the rest of the presentation and the webinar is going to describe. So the first question that most people have is, how much data do I need? How much storage do I need? The simple answer that most people will give you is generally larger data sets are preferred. But then you have a question, what is large? Okay. So for most good, for creating most good models, you would need close to 70 gigabytes of raw data, which gets translated to maybe 300 megabytes of processed data. Okay. But the more storage you have, the better it would be. So this particular number was obtained from this paper, which was an example for plant stress classification training for corn crops. And it was based on almost 10,000 samples and for 12 classes. Okay. So if you want to bring your own data, so to speak, let's say I have a farm or I have this test farm and I have collected so much data from there. So this kind of gives you a guideline for how much data you need to bring in. Now, if you bring in this much data, how much compute time will it take? Because you need to get those resources from these HPC centers. So how much computing time will it take to train? So obviously, the time it takes to train will depend on several factors like the size of your data, what is the hardware you are running on. So if you have a very old GPU or a CPU like maybe a K20 or a K40 from NVIDIA versus maybe a GB100, the amount of compute capacity is vastly different. So the amount of time it takes will also be different. Okay. So the previous slide, these were shown on A100 NVIDIA GPUs. Newer hardware will probably be 2 to 3 times faster than that. But in general, if you want to get an idea for the, let's say, training time, this is the time that it takes on this particular corn data set that you saw here. So this is training in terms of hours if you're using one GPUs as opposed to multiple GPUs and the amount of speed up that you can get. So for that particular data set, you see that it'll take maybe 8 to 9 hours if you are training on one GPU, and maybe less than maybe 20 minutes or so if you're training on 16 GPUs. Okay. So that kind of hopefully gives you an idea for the amount of computing time and cost you will incur. Now, how much money you would spend if you do it on maybe the San Diego supercomputing system, the Ohio supercomputing system, or AWS? So this kind of gives you an overview of that. So Ascent and Cardinal are two of the newer HPC systems at the Ohio Supercomputing Center. This is the hardware specification. So this table gives you kind of a high-level overview of the hardware that is available on these various HPC and cloud instances. So these two are HPC instances. These two are cloud instances on the Amazon Web Services. This indicates the kind of hardware that they have. So mostly these are like newer hardware. So these two systems have the NVIDIA's Ampere or A100 GPUs. These two systems have NVIDIA's H100 or Hopper class of GPUs. This indicates the dollar per node hour. So if you want to get one node on this particular system, how much money per hour you would pay for compute and how much you would pay for storage for so many terabytes per month. Okay, so these are numbers, and these are based on data collected in December of 2024. Again, things can change dynamically, but these were accurate as of December 2024. Okay. So in general, cloud systems have better, let's say, scalability because some HPC systems tend to limit the maximum number of nodes you can allocate. But also note that cloud systems have additional charges for, let's say, egress and ingress as well. So that is something you need to keep in mind, which typical HPC systems don't charge you. So overall, how do you compute the cost? So based on the prior corn dataset example, um, we found out that the Cardinal system at OSC has the best value compute. And in general, as the amount of compute time that you, let's say, spend on increases, the storage cost tends to kind of become negligible because storage is mostly constant once you have collected the data. The compute is the time which keeps on increasing. So hopefully this gives you an idea for the compute, storage, as well as the overall time it takes for you to run the entire pipeline on one of our supercomputing systems. Okay. So with this, we have kind of demonstrated the entire ICICLE cyber infrastructure for digital agriculture. Next, I would like to show a video demonstrating how you can utilize the entire pipeline on some locations like the San Diego Supercomputing Center or the Ohio Supercomputing Center. So note that both of these have been deployed on both locations, and the video that I'm going to show right now has more details on the actual use cases. Let me share my audio as well. I do not think I shared my audio, so give me just one moment here. Um, to share sound. Yeah. So hopefully now you should be able to hear the sound as well.
Welcome to the future of agriculture. This is ICICLE's AI cyber infrastructure for end-to-end processing of digital agriculture use cases. As a user of this framework, you can easily compose and manage your jobs all from one convenient and user-friendly interface, which is connected to an HPC backend where your jobs will be accelerated on modern GPUs and CPUs in a distributed fashion. Let's get started. The dashboard is your control center. Here you can select from many modules to compose your new jobs. Depending on the nature of your job, you can take advantage of one or a combination of modules, including data collection and preprocessing, image labeling and high-performance model training, model inference, and visualization of results. The dashboard provides a comprehensive overview of your resource usage, data storage, and processing times. Let's walk through an example of creating a job which uses all of these different modules. The use case here is classification of growth stages in a cornfield, where the goal is to train and use a deep learning model to analyze phenotypic data and provide detailed insights on the growth stage. Let's create the new job. The first stage is data collection and preprocessing, where you can import your data from Model Commons or upload it from your edge device directly. Once the preprocessing is done, we will have access to download and examine the preprocessed dataset. For now, let's move on to the next step, which is the model training. This page shows a list of model training options. The values will be populated by default for beginner users. At the same time, advanced users can adjust the training hyperparameters. The domain expert will then provide a number of labeled images for each class. This current page shows the first growth stage class, as shown in the very top. We can navigate through the samples and select representative images. Then we'll click Submit to move on to the next class to be labeled. Once the images are labeled for all the classes, distributed DNN training will be submitted automatically on behalf of the user. For inference, the user can select the inference task they wish to perform. In here, our task, again, is growth stage classification. Then we can select the model to use for inference. We can hit Submit, and that will take us back to the job overview page. Now, let's go to the final stage, which is visualization. The heat map is a view of the entire field. There are several blocks, each one of them is color-coded based on its predicted growth stage. The user can click on individual blocks, review the zoomed-in images, and provide feedback to the system if they think the classification is incorrect. Finally, let's look at the results gallery. Here, the user can examine individual images, their predictions, and the confidence score provided by the deep learning model. This job is now considered complete, so let's quickly go back to the dashboard. We can see the updated account statistics with the remaining SUs and storage. The new job list now shows the job that was just completed, and the user always has the option to go back and visit completed jobs. This concludes our overview of the framework. So thank you very much for listening.
So that is an overview of the pipeline that we have created in action at the Ohio Supercomputing Center. So it is available for use if anybody is interested. So you can use it on the San Diego Supercomputing Center as well as the Ohio Supercomputing Center. Please contact us for getting access and as well as more details. Finally, I'd like to conclude that webinar here by acknowledging all the ICICLE participants, faculty, students, and staff spread across 14 different institutions across the United States. And I'd like to open the floor up for any questions that people may have. Thank you.
Yeah, I think people can unmute themselves and ask questions. That might be the simplest, or please post question on the chat.
Hari, that was a great presentation. This was super useful for me. I'm trying to figure out how I'll be able to use this tool. So I'm going to be diving in and trying to use this on the Ohio Supercomputer Center. And I'm wondering, I actually, as I go back to work on this, if you will be making this presentation available so I can reference this in the future.
Yes, so Nilima has recorded this presentation. It will be uploaded to the ICICLE YouTube channel. Probably you should be able to see that in a couple of days. And feel free to email us. We are here and we are more than happy to work with you. And you in particular are an ICICLE educational fellow. So yes, do feel to email us and we'll be more than happy to work with you. Thank you, Matthew.
All right, thank you.
Sure. I think Mohan had a question about
Yeah, go ahead.
he would like to know about the actionable insights. So let me give this example. Suppose I am driving this, let's say a tractor. So we have a bunch of tractors fitted with GoPro cameras. Suppose I am driving this tractor on the field to take, and this tractor is doing tilling. So it is plowing the field to make sure that the soil aggregate is kind of evenly broken down and the crop residue cover is good and even. Now I'm going to take an image of my pre-tilling and post-tilling ground, and I'm going to see what areas were tilled properly and what areas were not tilled properly. Okay. Now this image will be transferred from the tractor to a laptop, as I had mentioned earlier, which will go to the ICICLE service running on the HPC system. It will, or maybe even on an edge system, depending on how it has been configured. And the result of the inference will be a shapefile. Okay. So what is the shapefile going to tell us? The shapefile is going to tell us which areas of the farm, which GPS locations, which latitude and longitude were not tilled properly. Okay. Now, the tractor that we have at Ohio State and most modern tractors are able to accept this shapefile as an input, and they're able to do some actuation. In this particular case, the actuation could be pushing down a tillage tool when the particular GPS coordinate is reached. So now the farmer can upload the data to a tractor, just drive the tractor. Okay. When the appropriate GPS coordinate is reached, the smart tractor is going to push down the tillage tool so that that particular area gets tilled again. Once that area is gone, the tractor is going to pull up the tillage tool. This is one use case. You can imagine another use case where the tractor can actuate a spray nozzle to perform precision spraying. Instead of spraying the entire field, I can now spray just particular GPS coordinate locations, which will be very, very accurate, maybe like a 1x1 square or a 2x2 square, and just spray in those particular locations, which will significantly reduce the amount of chemicals being applied on the field, which will also result in dollars saved for the farmer. I hope that gives you some idea about the actionable insights that we are currently generating. One other thing I would like to note is that the Ohio State University has an annual farm sciences review that happens slightly west of here at the Molly Karen Agricultural Institute. We are planning to demonstrate these pipelines and how this actionable output happens as live demos during that farm science review in September.
Hari, are those dates identified? If so, you can post it or let others know.
The final dates and times have not been posted. The dates for
Okay.
the farm science review itself is known, but
Okay.
we are still working with the organizers to figure out when exactly this particular demo is going to get scheduled. So typically, a lot of large ag tech companies as well as farmers in and around Ohio visit that particular location. Once those dates are finalized, all of us will be hearing from Neelima, and she'll be posting an update to our mailing list.
Sir, Mohan here. Thank you
Yes.
so much for the opportunity to actually, know all of these things. I think 2018, where I was developing a precision-based agriculture app, which is upon acting, using the data in IIT Madras Research Park. So
Okay.
so we were doing this, actionable intelligence related aspects actually with
Very nice.
predictive using the predictive analytics and data from the farm and the field and the best algorithms from the agri-tech. But this using the HPC and AI combination, very much interested. So is it possible that we can collaborate? Any chance, sir?
Yes. I think I'll leave that over to.
Yeah. Yes, Mohan, thanks a lot. Yes, ICICLE has a very open collaboration strategy. Please send us a note if you go to ICICLE website and there is an engagement link,
Okay, sir.
and take a look at that. And you can just, might be Nilima can post that link. Please send us an email, either to me, Nilima, or Hari. My email, I'm just posting it here on the chat. And then we can discuss and see how to collaborate with you.
Thank you, sir. Thank you so much, sir.
Thank you
And
for the
I've,
questions.
yeah,
Sorry, go
no,
ahead, Neelima.
no, I have also listed all the other components, links to, if you all are interested to know more, feel free to email, and our contacts are there on the website as well. Happy to engage with you all.
Any other questions, comments? Okay. If not, I think let's give a big thanks to Hari and the entire digital agriculture team for putting all this, doing the hard work, and coming up with the software and then releasing, testing. Some of them are here, so and hopefully we'll be able to get engaged with a lot of external people so that the softwares can actually be used, and we'd like to get feedback from you to improve the software. So that is the process which we are trying to do in the coming years.
So I think we only chose one presenter because of like mechanics and logistics, but this is definitely a team effort. I was presenting here on behalf of a very large and very capable and talented team. So all appreciation, congratulations go to them. Any mistakes, that's mine. Thank you, guys.
Yeah,
Thank you
no,
all.
just one more announcement, Nilima. I think we have 2 more webinars coming up. Might
Yes.
be the smart fields and animal ecology is on
It's on
17th.
no, it's on 12th, next week. And we'll have our food systems as well presenting. I think that's still on hold. We haven't finalized, but most likely in the week of 16th or on 17th Tuesday, I believe. But
Yeah.
details will be found on our social media as well. And or if you're already part of our mailing list, you will see the flyer as well.
And the smart field is already has been
Yes,
posted up,
that
right?
has been
Yeah.
posted, advertised, and it's there are a lot of components also with the smart fields, with animal ecology, and also with mixed with digital agriculture. So
Yeah. Thank you.
Yeah. Thank
thank
you
you
all.
all for attending. Okay, bye-bye.
Bye.